what we're going to do is put all the different ideas that we've looked at into one basic curve sketching menu, I suppose. If we wanted to draw a particular function, how to approach it. Things to look for. And I guess one of the earliest ideas we looked at was points of discontinuity. Remember domain, range, things like that. Y equals 1 on x is a simple one, of course, but whatever's on the bottom of the fraction can't equal 0, so we know that x can't equal 0 in the domain, and in this particular one, y can't equal 0 in the range, because I've got a constant on the top of the fraction. Those sort of ideas we looked at. That created asymptotes. So it's something like y equals x plus 1 on x. Because 1 on x can never equal 0, the whole thing can never equal x. So we have an oblique asymptote at y equals x. Okay, so we've got some curve, y equals some function of x. So what we've now seen is we can use the calculus to help us get a better idea of the picture, where some of these important points are. And the first type we looked for were the stationary points. And they were the ones where the first derivative is equal to 0. And that gives us a horizontal tangent. So we end up with either a turning point or the other possibility, maybe a horizontal point of inflection. But most of the time we end up with turning points. And then we go and classify them then. Okay, well, what type is it? And then we combine that with the second derivative. We talk about concavity. So if we've got a stationary point, but the curve is concave down, arms go down, where's your head? Your head's at the top. So there's got to be a maximum turning point. And if it's a minimum turning point, if, again, stationary point, but concave up, happy parabola, where's the head? Oh, it's down the bottom. It's got to be a minimum turning point. And then if it wasn't that, 0.4. Okay. So if the second derivative is equal to 0, that's when we have a possible point of inflection. As I say, it's like it's the next layer up. When we were looking for turning points, we found possibilities by finding the stationary points, and then we tested them to see what type of stationary point they are. So the next level up, we use the second derivative, we find when that's equal to 0, and that finds our possible point of inflection, and then we test that to see whether or not it is a point of inflection. And as most people will test it by drawing up the table of values. But remember that idea that I mentioned yesterday about the third derivative. It's an unusual way of doing it, and if you do it that way, make sure you explain it very clearly. Now, a curve, this also helps us. Remember, the curve will be going up or increasing when the derivative is positive, and it'll be going down or decreasing when it's negative. So that can give us an idea of, well, what's the curve actually doing? Well, oh, it's heading up or it's going down. And the concavity, again, concave up, happy curve. If the second derivative is greater than 0, sad curve. No one likes to be concave down. We're going to sketch a curve. Let's go through the menu. This is just a polynomial, so I don't have to worry about any asymptotes or anything like this. There's domains all real x, everything's fine with a polynomial. Find my derivatives. There's my first one. And my second one. I'm also going to use the third one. So there's my third derivative, 6. Stationary points. Remember, you're putting together a solution here. We don't want to just see random equations on a piece of paper. You're explaining what you're doing as you go. So, okay, the first thing I'm going to do is I'm going to try and find these stationary points so then I can classify them. So you write down, all right, stationary points occur when dy dx equals 0. I suppose this is similar to our in geometry. When you write a line down, you write a reason. Why did you say this? Well, this is my reason. Well, it's the same sort of idea. Why am I solving this equation? Well, there's my reason. I'm solving this equation because stationary points occur when the derivative is equal to 0. Solving that equation, 2 possibilities there, 1 and 3. So let's investigate. You have a choice. You could do the table of values with the first derivative and see what's happening either side. But if it's easy to differentiate, which this one certainly was, it's quicker to use the second derivative. So at x equals 1, the second derivative turns out to be negative 6. So it's concave down. Concave down, stationary, my head's at the top. So 1, and when I sub back into the y equation to work out the y value, I get -1. So 1, -1 is a maximum turning point. Let's test the other one. Just a coincidence, it turned out to be 6. Happens a lot though. I guess it's to do with the symmetry of the curves. Greater than 0, concave up, therefore minimum turning point. The y value on that one turned out to be -5. All right, another thing I'm going to say about inflection points. If they don't actually ask me to find inflection points, I'm not going to worry about finding them. Okay? Because logic says, if I've got something that's concave up, and then I've got something that's concave down, somewhere in between it must change concavity. I'm not really that interested about where it is. Sometimes in a question they'll ask you to because they want to see whether you know how to find them. For the sake of the example, I'll do it here. So possible points of inflection occur when the second derivative is equal to 0. So 6x minus 12 is equal to 0. I have one possibility. I'm going to use the third derivative because it was easy to find. When x equals 2, the third derivative is equal to 6. So it has a value. So that's telling me there is a change in the second derivative. There is a change in concavity. 6 does not equal 0. So therefore, yes, it is a point of inflection. I've left a line out there, haven't I? I should have wrote in, therefore, there is a change in concavity. So therefore, there's a change in concavity. Because that's what we're basically saying. The third derivative has a value, so there exists a change in the second derivative. The only time there won't be a change is, of course, if it's 0. Because then we're saying, no, there's no change. It's equal to 0. Let's draw it up. 1, -1. 3, -5. Now, when you're doing these, make sure it matches with what you've found out, because you can pick up mistakes. Imagine if I had said 3, -5, and I worked out it was a maximum turning point, and the other one was a minimum, and I plot these points, and, well, that just doesn't make sense. So clearly I've made a mistake. I would go back and check my working out. You'd be amazed how many times I'll look at someone's graph, I'll look at someone's working, and it just doesn't match. Because when it comes to graphing it, they do the logical thing, but then their working out says the opposite. There's the inflection point. I'll put it in there. It looks like we've got a straight line, of course, because they all happen to be nice and symmetric. But remember, we're not playing dot to dot. It is a nice curve. Oh, y-intercept's always easy to find, so I'll do that. Don't know what the x-intercepts are. Wasn't exactly something easy to factorise, so I'm going to do a little cheat that we do in mathematics sometimes. There we go. I just won't go up to the x-axis. It cuts it somewhere up there, but I don't really care. So, there. But, yeah, no, well, see, I've got the arrow to say, well, it keeps going. So it is going to cut it at some point, right? I just don't care. Look, if the x-intercepts are easy to find them. If they're difficult, don't worry too much about the x-intercepts. Okay. 10F and 10G. Let's have some great fun curve sketching, because I just know how you love drawing graphs. So you're going to love these exercises because you just enjoy your curve sketching so much.